So this will be our second lecture for the Analog VLSI class. We were looking at feedback systems, and the module 0 that I talked about is looking at negative feedback systems. And we started off by looking at why we need negative feedback systems, because any system where you need to control something very precisely, you most likely get to use a feedback system, and that to a negative feedback system. So last class we saw the example of, suppose a person is riding a motorcycle. There are three things that you do. So you basically have, first of all, you do a comparison, or basically, in other words, you take the difference, right? You sense and compare. Okay? In other words, you do you sensing and compare. You have a target speed in mind. You look at the speedometer. You kind of check the reality at what speed you're going, but you have another speed in mind. So you compare you sense the speed at which you're going, and you compare. So let me just put it as sense and compare. Okay, we take the difference, and secondly, what do? We integrate the error, right? We integrate the error, and thirdly, what happens is we drive the output. Okay. Now these things are done basically in the case we started off with the more physical example, and we moved to an electrical example. So we will continue with that electrical example. So what was it that we wanted? We wanted V out to be equal to some K times V in. Okay. And now we are going to accomplish this using a negative feedback loop. Now you might ask, why not just directly put an amplifier of gain K? So we will come to it. We will understand what we will figure out, or what we will see is, if you build any amplifier on a chip, okay, it is very difficult to get a very precise value. The value can vary across process, across temperature, and with different variations. And so what happens is, it is very difficult to get very precise gain values, and that is why we use a negative feedback system. It will become more apparent as we go along in the course. Okay. So right now what we have is, basically we have an input V in, all right, and we need an output which is V out, which is equal to K times V in. And what we said was, we can have a summer block. Now we cannot compare K times V in and V out, right? Because if you already have K times V in to begin with, you don't need all the system. What you have is only V in. And so what you can compare with is nothing but a scaled version of 1 by K times V out. Let me just put it as a 1 by K block. Okay, so you compare, you take the output, you tap the output, you take 1 K times of it, and you want to make sure that this error, let's call it VE, goes to 0. And we saw that in order to do that, we need an integrator, right? And this integrator, in order to satisfy the dimensionality of the system, needs a constant whose unit is frequency. Okay. Now, why not? Some of you might ask the question, why take the error? Why not just take the error and directly feed it? Why do you want to integrate? Okay. So for that, let's study the system. We saw in last class that the block that will satisfy this is an integrator, because for a constant input, you want the output to keep ramping up. Right? If your error voltage is constant, you want, if your error voltage is constant, okay, let me put it like this. If your error is like this, you want your output to keep going up, right? And so what happens, let's study this loop. Let's say you begin with a certain thing. Let's say you, at the initial condition, okay, the value changes to a certain value. Now what happens is, the error is large here, okay, and initially what will happen to this integrator, basically if you have a constant error, if your error voltage across time is going to be constant like this, what happens to the V out? What happens is, we saw last class itself. What will happen? It will be a ramp. Now, what will be the slope of this ramp?
The value of.
Correct. So let's say this value is some V naught. What will be the slope of this ramp? Basically, it is integrating,
A
right?
naught.
Will it be just V naught?
Yes, sir.
It will be omega u into V naught, right? Because we have that constant here. Yeah, omega u into V naught. So that is the slope of this line. So what can we know about this integrator? So if you have a higher omega u, let's say this is for omega u1, suppose you come up with another system for the same input, if you have a omega u2 which
Sir,
is
I have a
greater
doubt,
than
sir.
omega, yeah.
Sir, as the error would, as the difference of V input and the output, V output by K is V, that is in voltage, sir. So why we are taking as coefficient as omega n, that is the frequency. So
Yeah, so this is an integration, right? So if you don't have this omega
yes,
u,
sir.
if you just only integration dt, so you have this factor of time. If you look at the dimensionality, you have there is into t. Let's say if there is a
Okay, sir,
if you
okay.
integrate, okay, so you have into t, but the output has to be voltage. So you need a constant which has a unit of second inverse. Okay.
Okay, sir.
Yeah. Yeah. So here, suppose you have a omega u2 which is greater than omega u1. How do you think the slope would be?
Phases.
It will be steeper, right? Something like this. So this will be your omega u2 and so on. Okay. Now, as we saw here, the slope basically depends on the product of these two. So if you want the slope to be faster, or in other words, if you want V out to, we will see that today hopefully, if you want V out to change faster, either your omega u has to be higher or your V naught has to be higher. Okay. All right. So now, having now what happens is what happens in the steady state. Okay, let's look at this steady state. What is steady state? That is, it has finished its transient response, right? So what will be the steady state response? That is, first, let's say there is some step input or whatever it is. Okay. At the end of the day, what will you get? This integrator will keep on integrating. So this is for an open loop I kind of showed, like if your error is the same. Now what happens is, initially when there is a step, the error is large, right? The error becomes high, and then what happens? 1 by k, this error also starts increasing, correct? The feedback signal also starts increasing, then the error starts decreasing. The characteristics of it we will see later. Finally, what happens when the whole thing settles? What will be the value of VE? Let's say the settling process has happened. So this is just ramping up. Then what will happen?
Vn minus V out by K.
Correct. But since it is a negative feedback system, right? What will this loop do to VE?
Sir, it will go to 0 at the steady state.
Exactly. At the steady state, it will go to 0. Why will it go to 0? Because as the error increases, this integrator is going to keep ramping up the voltage. As this error voltage, let's say I'm giving you a step here, okay, the error instantaneously becomes 0, and as the output keeps the error goes higher, and then as the output keeps increasing, the scaled output will also keep increasing. So now the error will start decreasing. Okay, and so the amount by which it integrates will also start decreasing, right? Because the slope, we said the slope is what? Omega u times V naught, correct? So as the feedback signal starts increasing, the error voltage starts dropping, and therefore the slope after a point starts decreasing, correct? And so this slope also starts decreasing, but nevertheless what is happening is it is slowly, the error starts decreasing but at a little slower rate, and finally at the steady state it will reach the value. So what is the steady state value? VE becomes 0 and V out becomes K times V in. Okay, now this integrator's output, one of the interesting things that we can see here is the output of the integrator. The output of the integrator becomes constant only when what? Only when the error voltage is 0. Okay, is this clear? It is an integrator. When will the integrator become a constant value? It will become a constant value only when the input to it is 0. Okay, if the input to it is negative, it will start decreasing. If the input to it is positive, it will start increasing. Okay, but the output of the integrator will remain constant only when the error voltage is 0. Okay, and so in the steady state, that is basically what we want. Your output, the error becomes 0, which implies that V out is equal to K times V in, or V out by K is equal to V in. Okay, so this is a generic principle that you would see in any negative feedback system. In the negative feedback system, the loop will strive hard to drive the error to 0. Okay, now all this we have done more at a little intuitive level. Okay, if you kind of look at the slope, look at the shape of the signals that I have drawn, what can you intuitively say? Like, what is the kind of response that the output is having to a step input? Is it a linear response, exponential response, or some cubic response?
Sir, logarithmic, little bit logarithmic.
Or in other words, yeah, correct. Okay, it has some behavior of e to the power of something. Okay, so this is more at a intuitive level. Now we will jump into math and then see if this is making sense. Okay, are there any questions, any doubts till now? It's a very simple system. Okay, and we are just trying to see how it works, because many of the analog circuits that we will be working with, or if you go to an industry you will be working on, many of the systems have negative feedback around them. Basically, you will have an op-amp and some negative feedback around it, and with that you will design maybe a filter, you might design an LDO, you might design whatever correction circuitry that you are looking at, calibration circuitry. So many analog systems are negative feedback systems, which is why we are kind of starting off with this. Okay, so all right. So
Sir,
let's, yeah.
Sir, can you tell why the rate decreases when it is about to reach steady state?
Okay, good question. So what is the rate? That's why we looked at this here. What is the slope for this system with respect, when I'm talking about the slope of with respect to time for the error input? So basically what I'm saying is, you have this omega u integral dt. Let's say you have some Vi here and Vo here. Okay, we are only looking at the integrator. For this particular integrator, what is the slope? The slope we said was equal to Vi into omega u, or omega u into Vi, correct? Now what is happening in this feedback system? As your input starts increasing, the feedback signal also starts increasing. Okay, so what happens to the difference between the input and the feedback signal? that will start decreasing, right? So let's put some values. Let's say this is 0 and this is 1 volt. Okay, you have a 1 volt step. So let's say initially it was in steady state and therefore the error was 0. Now this was also at 0 volt. Okay, when the step happens, what happens to the error voltage? The error goes to 1. Okay, 1 minus 0, it goes to 1. And therefore now this integrator starts integrating. Okay, and once you start integrating, this voltage also starts increasing. Now as this is a constant, this is constant at 1 volt, and the feedback signal is now increasing. So what will happen to the error? The error starts decreasing initially linearly. Okay, and then what happens? Now because the input Vi which is going into the integrator itself is reduced. Okay, let's say after some little bit of time, a few nanoseconds, let's say, it has come to, let's say, 0.8. Okay, now your Vi has decreased, and therefore your slope decreases. Okay, because of that, what happens? It starts charging little slowly, and then this happens, the error keeps decreasing, and therefore the slope also keeps decreasing. Okay, and that is why it kind of flattens out, as you go out. The slope keeps decreasing as you go ahead in time. Is this making sense? Is this clear?
Yes, sir.
Okay, all right.
Sir, are we not recording this?
Yes, we're recording this.
Okay, sir.
Yeah. So all this we just did it intuitively. Okay, so I wanted you to kind of have an understanding intuitively. Now let us jump into mathematics. Okay, now what is the error voltage we saw? Error voltage is what? V in minus V out by K, right? So V in minus V out by K is our error voltage. Okay, now what is
Sir,
our V out? Yeah.
Sir, instead of using integrator, can we add the error to the V in to get V out?
Add error to the
V in.
Okay.
So V out.
Now if you add, okay, let's see how that works. Okay, if you add the error to the V in, okay. Now let's say if you have a step function, now your error is 1. If you add the error, so you have a step function, this is V in. Now your VE also goes up as a step. Okay, this tail will not be there. Let's say it goes here. Okay, now if you add the 2, what will happen? It will become 2 volt. Now you will have again a negative error. So you will come back to this. But yeah, I am not sure. I mean, that can be another controller. Basically, if you look at control systems, you'll have this proportional integral controller and so on. But basically, when you are adding your input to this, I'm not sure how that works. Okay. In some control systems, you might add that along with the integral. Okay, but I think this PI controllers and all might have that, but probably not here.
Okay.
Yeah. Okay. So what is the output? Output is nothing but omega u times integral of VE dt. Correct. So it is nothing but omega u integral of V in minus V out by K dt. Okay. Now let's differentiate the whole equation, because we want to solve this equation and it's easier to solve differential equations. Okay, so dV out by dt becomes omega u times V in minus V out by K. All right, now let's move things around a little bit because we want to solve this equation. Okay, let's say dV out by V in minus V out by K becomes equal to omega u times dt. Okay, so let's do a little bit more manipulation. Let's just say dV out by K times V in minus V out. Okay, I'm just taking the K out this side. K V in minus V out is equal to K times, omega U times dt by K, right? Now integrating on both sides, what do you get? This has the natural logarithm of K times V in minus V out. The differential of the denominator, because V in is a constant, okay? Here we are assuming that V in is a DC voltage, okay? Now this becomes minus of this one because the coefficient of V out is minus. This is equal to, so we are integrating from the limits, basically from V out at 0 to V out at time t is equal to omega U t by K, okay. So the integration is from 0 to t, all right. So integrating from 0 to t, all right. So what happens? Let's transfer the negative sign the other way, okay. So we will have natural logarithm of K times V in minus V naught V out of t divided by K times V in minus V out of 0 is equal to minus omega U t by K, all right. Now how do we solve this? We take exponential on both sides, and therefore we have K times V in minus V out of t can be written as what? K times V in minus V out of 0, just skipping some, e to the power of minus omega U t by K, right. Now if you, what we are interested in is V out of t, right. So what is V out of t? V out of t can be written as, there are two terms here. We can say V out of 0 e to the power of minus omega U t by K plus K times V in 1 minus e to the power of minus omega U t by K, okay. Now what are we looking at here? There are two terms here, right. Basically all we did was to solve differential equations, okay. Now what is this term? This term is basically telling us that the initial condition decays, okay, exponentially, and we see here that the input is basically the output is rising up to the input in an exponential way, okay. Many of you now will recognize this form of an equation, right. So this is a first order system. If you have a RC filter or an R and a C system, if you give a step response to this, you will have what? You will have a, if let's say this is 0 to A naught, your V out can be written as what? V out of t can be written as A naught into 1 minus e to the power of minus t by RC, okay. This I hope you remember from your analog circuits or whatever courses you have done in your undergrad, in your previous semesters, okay. So this is the exponential behavior that you typically see in any first order system. If you take any RC system, any RL system, any first order system will have this this exponential behavior, okay. If it is charging up, it will be 1 minus e to the power of minus some time t by time constant, okay. If it is a discharging system, it will be just e to the power of minus t by time constant, right. So comparing this, okay, with a typical first order behavior, first order system behavior will be what? Let me say first order behavior, let's just call it. For the first order system, okay, you have this kind of an exponential behavior. You will say e to the power of minus t by tau, okay. In the case of an RC system, this type of an RC system, tau is RC, okay. Now if you compare this and this, what can we say is the time constant? time constant of this amplifier can be written as what?
K by omega u.
Correct. K by omega u. Is this making sense? Okay. So previously at the beginning of this class, we gave a step to this system and we just worked our way around the loop, and we kind of predicted that, you know, there will be changing slopes, and if you intuitively we said like it will look something like an exponential. Okay, because initially you have very large error for the same integrator. Okay, you have a very good slope, and as the feedback loop starts working, what is happening is the error starts decreasing and therefore the slope starts decreasing. So it's like a cyclical process. Okay, the output increases, error decreases, slope decreases, and so it's like a vicious circle. Okay, the slope keeps on decreasing as time goes on. Okay, and that is predicted by this exponential response. So I am pretty sure that all of you are familiar with exponential response. If not, for the sake of completeness, let me just draw it. Okay, so let's say this is our V out, and what we are doing is, let's say if you have this is our desired V naught, the output behavior is going to be, okay, so case one, what I'm saying is V out of 0 is 0. Okay, if you say V out of 0 is 0, V out of t will become what? V out of t becomes, the first term becomes 0. The first term becomes 0. The initial condition is 0. So k times V in into 1, the output becomes k times V in into 1 minus e to the power of minus omega u t by k. Right. So it follows this exponential behavior. Now, what is the significance of tau here, or the time constant here, which we defined as k by omega u? So for after 1 tau period, okay, it would have, how much will be there? Let's say I think 1 tau should be put a little, I think it's some 78 point some percentage, right? Okay, let's take an example. Okay, let's say k is equal to 5. Okay, omega u is equal to 1 gigaradian per second. Okay, and V in is, let's say, 1 volt. Okay, can you find out and tell me what will be V out at t equal to tau? Can you just quickly calculate? And let's say what is V out as t equal to 3 tau, and what is V out at t equal to 5 tau? Can you guys, maybe you can use your calculator. If you haven't got your calculator, you can use some calculator apps or your mobile or whatever. Okay, so k times V in is 5 volt. So 5 into 1 minus e to the power of so at t equal to tau, the exponential becomes 1 minus e to the power of minus 1, right? T is k by omega u, so it becomes this. In the other case, it becomes 1 minus e to the power of minus 3. Okay, and this 1 minus e to the power of minus 5. Okay, if you just see what is 1 minus e to the power of minus 1, what do you get?
Sir, t equal to tau, the value of V output equal to 3.16.
Correct, 3.16.
And
Here?
t equal to 3 tau, the value is 4.75.
How much? 4.75. Yeah, okay.
And t equal to 5 tau, it is 4.96.
96. Okay. So if you look at the percentage wise, this is 63.2 percentage. Okay. And if you see what is 1e minus 2, it is 86 point, sorry, for 3, it becomes 95%. Okay. And for minus 5, it becomes 99.3%. Okay. So in other words, what are we understanding here? Okay. If you want, if you wait for time equal to t equal to tau, you will have 3.16 here. And if you wait for 3 tau, maybe I should draw it a little differently. Okay. Let's say if you are waiting for tau, let's say this is some 3 tau and this is some 5 tau. Okay. Here the value is 3.16. Here the value is, let's say, 4.75. Here it is 4.96. Okay. In other words, if you wait for one time constant, it rises up to 63% of your final value. Okay. If you wait for 3 time constants, the error is only 5%. Right. If you wait for 5 time constants, the error is only 1%. But theoretically, you say that it only asymptotically reaches the final value. Any first order system reaches the final value only asymptotically. That is what at t equal to infinity only it becomes, error becomes absolute zero. Okay. But for all practical purposes, okay, we cannot wait for infinite amount of time. Right. We only have to set a limit. If you say 95% is enough for me, then you say the time, the settling time is 3 tau. And if you say I want an accuracy of 1%, your accuracy, you have to wait for approximately 5 tau. It's some 4.8 tau, something like that. Okay. So what does this tau tell us about this first order system? It conveys the idea of how fast my amplifier is going to respond to changes. Suppose there is a change in the input. Okay. Some change, some step change, or maybe some ramp change, or any other change. Okay. Now, how fast is my system going to respond? Okay, is what is given by this tau, or in other words, this k by omega u. So, what can we say about the omega u? If you have, let's say, a system where omega u1 is greater than omega u2. Okay, let's say this black line is for omega u1. Now I am telling you that omega u2 is smaller. How do you think this time domain response will look like? Let's use another color. Same system, okay, same feedback loop, k is the same. Okay, all what you have done is, let's say omega u2 is, instead of 1 gigaradians per second, let's say it is 0.5 gigaradians per second. Right. Now what happens to the system? How will the settling be?
Will settle later.
It will little slower.
Yes, sir.
It will take more time, right? So your tau here itself has changed. Okay. So let's say it is going to settle something like this. Okay. So what we see here is, now we are kind of looking at the behavior of the integrator. We are trying to understand how does this integrator play a role in our system. Okay. Initially we just said that omega u is the constant. Okay. But what do we understand here? Omega u plays a very large role in determining how fast your amplifier is going to behave, how fast your negative feedback system is going to behave. Okay. If you want really fast response, what should be the thing? What is the value? What is the relationship between tau and omega u? It is k by omega u. So for larger omega u, you get tau is smaller, which implies that settling is faster. Okay, and vice versa. Okay, all right. So does it make sense? Is it clear?
Yes.
Yes. Okay. All right. Now, so now we have seen one important part, which is the speed of the amplifier. Okay, and another thing is also, let's look at the other factor. What else determines this settling response? Tau is dependent on omega u, we saw. What is the other thing? What is the other parameter that tau depends on? It is K,
Okay.
right? So what can we say about K? For, let's say, K1, let me give K1 greater than K2 greater than K3. There are 3 gains. Okay. Now same integrator, all what we are doing is we are changing the feedback ratio. Okay. If you change the feedback ratio, having K1, K2 and K3, okay, how will tau 1, tau 2 and tau 3 behave? How will their, which tau will be greater?
T1 will be
Tau
greater.
3.
Yeah,
Tau 3.
tau 1 will be greater than, tau 2 will be greater than tau 3. So obviously the settling time, this will be the slowest in terms of settling, and this will be the fastest in terms of settling. Okay, so if you want to kind of draw this thing in the same graph, let's say the x-axis is t, and let's say this is your V out. Okay, let's say this is K1 times V in. Let's say this is this is K2 times V in. I said K1 is greater, right? This is K3, and this is K3 times Vn. Okay. Now the settling will be such that this will settle faster. Okay. And what will be the initial slopes will be the same. Okay, because when you look at the integrator, okay, well, what will happen is, okay, the initial slope will also be different because you're having a larger error here. Okay, so for the same omega u, you'll have initial slope will be faster, but then it will take more time to reach the final output. Okay, same way, if you look at the K3, okay, the initial slope will be little faster, because what did we see about the initial slope? If you remember, when we looked at that this particular thing, we said that the slope depends on omega u and the error voltage here. Okay, so for a higher K, the error voltage is going to be larger, right? So it is going to start with a higher slope, but then what happens is ultimately it will take a longer time to settle. Okay, so settling depends on 2 factors, which is, one is the omega u. We will see that omega u is also called as the unity gain frequency. Probably we will do that next class. Okay, but also, not only does it depend on omega u, it also depends on the value of the gain. So for any negative feedback system, analog system that you see, if it's a first order system, you will see that the integrator's omega u, okay, we will see that it is the unity gain frequency or the unity gain bandwidth of the integrator, that as well as the division ratio or the feedback factor, both of them play a role in determining how fast your settling happens. Okay. Now let me ask you another question. Even for K3 times Vn, if you want faster settling, what can you do?
Sir, instead of writing K1, you have written K3.
Oh, I'm sorry. That is my mistake. Yeah, this is K1. Yeah, I changed. Yeah, K1. Suppose we want faster settling for K1 times Vn. Okay, faster than this. And let's say the rest of the system is at your disposal. What can you do?
Increase
Increase
omega
omega.
Increase omega u. Okay.
u.
So depending on the particular application for which you're designing your analog circuit, okay, you have to trade off these things. Okay. Suppose you have very larger steps that you are looking at, you have to make sure that the omega u becomes higher so that you are able to maintain the time. Okay. Many times you will have requirements such that saying that my amplifier or this particular system has to settle within, let's say, 0.5 nanoseconds or 500 picoseconds. Now you have to build your negative feedback loop. You have to design each of these elements such that, you know, and my accuracy is, let's say, 1%, which means 5 tau. Let me just give that example and close this class. For example, okay, let's say my settling time is 500 picoseconds and my settling accuracy is 1%. Okay, then what will I have to do? I have to make sure that if you calculate exactly for 1%, I think it is some 4.6 tau, okay, or roughly 5 tau. Okay, 4.6 tau is equal to 500 picoseconds. Now from here you get what is your time constant, okay, and from this time constant you go to what your you know what is the K, you already know what is the K, you find out what is your omega u. Okay, now with this omega u you go ahead and design your integrate. Okay, so usually analog design starts at the top down approach. First you look at the whole loop by itself, look at the loop dynamics. We will look at other aspects of this loop also in the following classes. Okay, but the way you design circuits is, first you start off with the top level system. You see what is the settling behavior. Is it a first order, second order, third order system? Look at what are the time constants involved there. And for the given condition, let's say you want a gain of 100, obviously you have to have a higher omega u. Okay. All right. So any questions? If not, we will wind up today's class.
Sir, can you go to previous page
Yeah.
showing the exponential behavior
Yeah.
before this?
Oh, before this, okay.
Before this.
Okay.
Sir, so this
one?
initial condition decay,
Yeah.
does it change, affect anything like initial slope or?
It will. So basically, what it means is, like, suppose I think I have not shown that somewhere here. Okay. Suppose, let's say, yes, it will. Okay. Let's say this is from 0 to, let's say, 5 volt. All right. Now, suppose your initial condition is you are starting from 2 volt. Okay. Now, first of all, your initial slope will be different, right? Because the error is now, instead of the initial error at time t equal to 0 plus, your error is not 5 volt, your error is now only 3 volt. Okay. So obviously your initial slope will be different. Okay. And it will be something like this.
Okay, sir.
Okay. So basically this is a more generic system where you take care of the initial condition also. All right.
Okay, sir.
Yeah. Okay. So any other questions? All right. If not, thank you everyone and have a nice day.